Next, we will take a look at one of the most popular and practical machine learning algorithm, gradient boosting. It is a generic ensemble method. It can be applied to many modeling algorithms with varying levels of success. For example, the gradient booster trees such as XGBoost, LightGBM, and so on are quite popular because they often outperformed competing methods in head-to-head competition. And as you all aware, in the case of Kaggle competition, we could see most of the winners use the XGBoost or Light GBM. With that, they are able to achieve higher accuracy. Next, we will take a look at what exactly gradient boosting is all about and what makes this algorithm so special in achieving the higher accuracy. What is gradient boosting? It is an ensemble algorithm like random forest, but there is a huge difference between random forest and ensemble, the gradient boosting algorithm. But these algorithms, the gradient boosting, random forest, falls under ensembling algorithm category. But there is a difference between these two. So the gradient boosting algorithm is used for both classification as well as regression problem, but also it works well with the ranking. There are search engines that uses the variance of gradient boosting. The idea of gradient boosting is it combines multiple weak learners into a single strong learner. So here the trees are built one after the other. So these trees are called as weak learners. The trees are created in sequential to correct the mistakes of the or the residuals of the previous trees until it reduces the errors to the great extent. That's the idea of this one. Like AdaBoost, the gradient boost build fixed size trees, but unlike AdaBoost, each tree can be larger than a decision stump. Just to help you to recall, in AdaBoost, it uses the decision stump. It creates the decision stump. The decision stump has a root node, and it will have only the two leaf node in it. Whereas in the case of gradient boosting, the trees are grown to a greater depth, usually ranging from 8 to 32 terminal nodes. Now let's go ahead and understand how this gradient boosting algorithm works for regression. To understand the gradient boosting algorithm, so we are going to use this data set. This data set has three independent variables: the height, favorite color, and gender, and the target attribute. The dependent variable is weight in this case. As a first step, it fits the first model to the original data. So this, let's say it's a first model. The first model considers the first prediction as the average of our target variable. The average of this target variable weight is 71.2. So this is the predicted value. So this one sounds bit weird, but this is how it works. For all the observations, the predicted value is 71.2. So in this scenario, the 71.2 is the average of our target variable weight, and this average weight is used to calculate the residuals. If you see here, the predicted weight for all the observations are the same, and with this we are able to compute the residual. This is called my first residual. I call this a first residual. It is also called as a pseudo residual. What is residuals? Residuals are the difference between the actual and the predicted value. So with this first residual, it builds a new decision tree for which the independent variables are same. This is my second model. For this second model, the decision tree, the independent variables remain same: height, favorite color, and gender. These three independent variables remains as it is. But whereas the target attribute is residual, not weak, it is residual. Even this part also a bit confusing, but this is how it works. So it considers the residual as the dependent variable. And if you look at the terminal nodes, the leaf nodes here, you can see the residuals here, 16.8 and 1.8 and 5.8, negative 14. So all these residuals, you can find it in the leaf node here. The idea of considering the target attribute residual in this case is to predict the errors. I call this second model and second iteration. The second iteration, it predicts the error. It predicts the error. So this decision tree looks like gender is equal to female as our root node, and this height is less than 1.6 and not blue. These two decision nodes are child nodes. And these child nodes have the leaf nodes here, few leaf nodes here. For the sake of simplicity or to simplify your understanding, in this case I've used only 4 leaf nodes, but it is common to allow anywhere between 8 to 32 leaf nodes. So if you look at this here, the gender on the left side of this one, if the gender is female, if the condition is true, it will go on the left side. The left side of this one is true, and right side of this root node is false. Similarly, each node here in this decision node, the true will we need to look at the true on this side, and the false, the predicted values for the false will appear on the right side of this one. And if you look at this, gender is female and height is less than 1.6. We could see that in for female there are 3 observations are there of the this one and the female this one, and we have 3 observations are there, 3 records are there female, but only these 2 records, because in this case the height is less than 1.6. Of these 3 female records, only these 2 records falls under this condition because the height is less than 1.6 for these 2 females. And the corresponding residuals, negative 15.2, negative 14.2. There are 2 residuals are there for this condition. Okay, so these 2 residuals will land into a single leaf node because of the limitations of the leaf nodes. In this case, we have only 4 leaf nodes. Hence, what happens? These 2 residuals land into this one. Okay, and similarly here, if you see here, gender is male, female, it's false, it's a male, and it is not blue, which means male. We have 2 male records with color not equal to blue. So red, green, we can see the red and green, the male, and 1.8 and 5.8. These 2 residuals land into this leaf node. For those leaf node, those leaf node have more than 1 residuals in it. So it computes the average for that leaf nodes residuals, and then it replaces these residuals by the average value. So in this case, if you take the average, negative 14.7. If you take the average of this one, you will get 3.8. Okay, the next one is the predicted value. What is the new predicted value? So we have fitted with the data base data. So this is my first model, is I call this a base model or base model. Okay, so now to find out the predicted value, so you need to add the previous model's predicted value, and then for this first record, let's see, let's take for example for this first record, what is the predicted error as per this tree? So he's a male and is a blue, right? So male, gender is female. It's not female, it's a male. Okay, not blue is false. Yes, it's a blue. And 16.8. This is the residual for him. This is the predicted residual, and the previous model's predicted value is 71.2. If you add these two things, we get 88. This value is the predicted weight. Predicted weight is 88 in this case. The predicted weight and the actual weight, both of them are same. So it is good, but it is not good because we have low bias, but probably high variance. It can lead to some kind of high variance. To deal with this, now it is utilizing gradient descent, wherein it uses a parameter called learning rate. Step. Learning rate is also called as a step. This step, the learning rate. So in this case, what we do is instead of adding the predicted error with the previous model's predicted value, we multiply this predicted error by the learning rate, zero point 0.1. In this case, I have chosen the smaller value, 0.1. So take the product of the learning rate with the predicted error, and then add this with your previous model's predicted value. This one will give you the new predicted value, 72.9. So now you have a new predicted value. And if you take a look at here, so now we can, with this predicted value, you can compute the residual, the new residual. And if you subtract the predicted value 72.9 from 88, you get 15.1. Similarly, if you do it if you follow the same approach, so we can see the new residuals or something like this. For simplicity's sake, I just took only one record. Okay, so the 15.1. So compared to the first model's residual, the second model, and after introducing the second model, the sequential model, after picking up the first model's residual, and now the residual got reduced, 15.1. In this case, we have included the second model with the first one, right? So the first model plus learning rate 0.01, sorry, 0.1 into the predicted error. So this is the one gives the new predicted value. With the new predicted value, we are able to compute the new residual. As the trees are built in sequential, iteratively, we could see that there is a improvement in the sense reduction in the residual. Compared to this one, the reduction got reduced. Sorry, the residual got reduced. And compared to the previous predicted error, this predicted error is, sorry, predicted values, predicted weight, and previous predicted weight, with the current predicted weight, you see that there is an improvement. It is somewhat closer compared to this one. Similarly, when we keep doing this, the algorithm keep doing this, it keeps building the new, it keeps building the, the trees in sequential iteratively in order to reduce the error at the great extent. That's the whole idea of the gradient boosting. So here in this case, the first step is, look here, in this case, I put together everything in a single slide so that you can understand quickly. In this case, we fitted the base model to the original data. So for this, it considered the predicted weight, the body weight, as the average of this column, 71.2. And if this is 71.2, if you subtract this one from this actual value, the residual is, the initial residual is 16.8. The initial predicted value is 71.2. And then it builds another model in sequential. And then here, with this model, predicted error is 16.8. When we add this predicted model with this first model, we can get the new predicted value. But it is not advisable adding the second model's predicted error with the first model's predicted value. Instead, you multiply this predicted error with the learning rate, and then if we add it, you get the new predicted value as 72.9. So multiply the predicted errors by learning rate for each observation and add it with various prediction. So that one will give you the new predictions. That is the whole idea of this one. And in the third iteration, if you see here, so here the new predicted value is 32.9 and the new residual is 15.1. And then it builds a new tree in, new additional tree here, so in sequentially. So in this case, the predicted error of this tree is 15.1. So if you multiply this one with the learning rate zero point 0.1, and then if you add this value with the second model's predicted error multiplied by the learning rate, and if you add this with your first model, you get the new predicted value. This has to be done iteratively as long as the errors are reducing it at the great extent. It has to be iterated. Okay, fit the base model to the original data, and then fit the next tree to the residuals of the previous, and then take the difference between the target value and the prediction of the with the new prediction of the model, and fit the third model. That is what it has been done so far. And the final model, this final model aggregated the result of each step. It aggregated the result of each step, and thus the strong learner is achieved. I call this a strong learner because here the residual got reduced. So for instance, in the case of mean squared error can be used for a regression task, and in the case of logarithmic loss, in the case of a classification task, logarithmic loss can be used. And last but not, it is worth noting that the existing trees in the models do not change whenever a new tree is added. So this one will not get disturbed. Okay, it will not undergo any changes when a new model is included in this existing ensemble. So that is pretty much it. Next, we will take a look at the mathematical representation of the gradient boosting. And followed by this, we'll take a look at the gradient boosting algorithm steps for classification